Hello. So this is our project on interpretable hybrid models for visual pattern recognition, developed as a part of the pattern recognition and neural networks course. The goal of this project is to study how neural network-based features and classical pattern recognition features can be combined while also addressing the interpretability of deep learning models. So the dataset which we used over here is the fashion MNIST dataset, which has 28 cross 28 grayscale images, including 10 clothing categories, and it has training samples of up to 60,000 images and 10,000 test images. So that's all about the dataset overview. So the environment and execution check project is as shown over here, is implemented in PyTorch and runs using Apple's Metal backend. All the results shown here are generated from a working and executable pipeline. Um, um, Moving on to the baseline CNN model. So um, we first train a baseline convolutional neural network using the ResNet 18 architecture adapted for grayscale images. And this model also serves as our neural baseline for comparison. As you can see, the baseline CNN model is loaded. Uh, in the meantime, I can show you what the baseline CNN model is. So this is the baseline CNN model that has been loaded over here in the notebook. Coming on to the baseline CNN accuracy, this accuracy represents the performance of the standalone neural network and serves as a reference point. And as you can see, the accuracies of looping 92%. So um, explaining the CNN explainability, we've taken, let me split it into four parts. We've taken a sample image. Although the CNNs achieve a good accuracy, they're often considered black box models, as as it is seen over here. So, in order to address this, we apply multiple gradient-based interpretability techniques such as the GradCam heat map, the saliency map, and the integrated gradients map. Uh, this is the GradCam heat map as shown on the screen. So the GradCam highlights the spatial regions over here that contribute most to the prediction. Coming on to the saliency map shows the pixel level sensitivity of the output with respect to the input. And onto the integrated gradients, it provides a more stable attribution by accumulating gradients along an interpolation path. Um, so altogether, these methods help us understand how the CNN makes decisions, not just what it predicts. As you can see, the consists of 60,000 training samples by loading the 20 cross 20 tensors. And onto the hybrid model motivation. So to combine the neural networks with classical pattern recognition, we built a hybrid model. We extract deep CNN embeddings and combine them with handcrafted features such as HOG and GLCM, which capture edge and texture informations. As you can see over here, we are extracting the hybrid features in the cell, and onto the results. The fused feature represent is classified using a random forest, which provides both strong performance and inherent interpretability. Just shown a cell of confusion matrix, and onto the SHAP explainability. To further interpret the hybrid model, we use SHAP and random forest feature importance to quantify the contribution of individual features as seen as shown in the image over here. This allows us to analyze how both handcrafted and neural features influence the predictions. As you can see, this is a sharp scatter and this is a sharp explainability. And in the end, we've generated an accuracy comparison between the baseline and the hybrid model. Overall, the hybrid model achieves comparable or slightly improved performance while offering enhanced interpretability compared to the baseline CNN. To conclude this project demonstrates how classical pattern recognition techniques and neural networks can be combined to improve transparency without sacrificing without sacrificing accuracy. And the hybrid approach provides both predictive performance and meaningful interoperability, which are the key goals in modern pattern recognitions. Thank you.